Now let's take a look at the Firefly protocol. As shown in the table at the lower right of the slide, it is a three-state update protocol. When a bus update transaction occurs, the Dragon protocol updates its caches, but not main memory. Suppose that main memory was also updated. Then which state don't we need? There would be no need to distinguish between SC and SM. Dragon only keeps track of which cache is in SM, so it knows which cache is responsible for updating main memory when a block is purged. But there is a potential advantage to having a fourth state. What is it? It might take longer to update main memory than to update caches. Write buffers are normally used to avoid stalling the processor on a write reference. But write buffers do overflow, and they are more likely to overflow if every change to a shared cache line has to be written through to main memory. But note, this is not as bad as write-through. Write-through writes all writes to main memory, not just writes to shared cache lines. The three states in Firefly are valid, or V. This is the same as the exclusive state in Dragon. Shared, or S. This is the same as the S in our invalidation protocols. Multiple caches may be holding the block, and main memory is up to date. D, or dirty. This is the same as the M state in our other protocols. Only one processor has the block cached, and it has been written to since being brought in from main memory. If there is a processor read miss, called in this diagram CRM for CPU read miss, and the shared line is not asserted, then the block is brought into the cache in valid state. If there is a CPU read miss and the shared line is asserted, the block is cached in state S. If there is a CPU write miss and the shared line is asserted, the change is written through to main memory and the block is cached in state D. If there is a CPU write miss and the shared line is not asserted, the block is cached in state D. In this case, the write is not written through to main memory. If the block is in state V and there is a CPU write hit, the block transitions to state D. If the block is in state D and there is a CPU write hit, the block stays in state D. If the block is in state S and there's a CPU write hit, what happens depends on whether the shared line is asserted. If it is, the block stays in state S and the change is written through. If it's not, the change is written through and the block transitions to state V since it's not being shared any longer. If there's a CPU read hit, the block stays in whatever state it is already in, just like in the Dragon protocol. Now, let's consider the bus-initiated transitions. If the block is in state S and another processor reads or writes it, that is, a bus read or a bus write occurs, the block stays in state S. If the block is in state D and another processor reads or writes it, it transitions into state S. As we've already said, the change is written through to main memory. If the block is in state V and another processor reads it, it goes into state S. What happens if another processor writes it? Well, we know it won't be invalidated because this is not an invalidation protocol, so it must be updated, and since it is now being shared, it also goes into state S. That is not shown on the diagram, however. When our animation starts, all caches are empty, and the value of A in main memory is 1. Processor P1 reads A, but A is not yet cached. This induces a bus read transaction. The memory controller responds with the block. The block reaches P1's cache. The state of the line is set to V, since the line has not been modified and is not held in any other cache. This completes the read operation. P1 then writes A, changing its value to 2. This is a cache hit, but the cache has to change to state D. The write operation completes. Now P3 tries to read A. This causes a cache miss, so a bus read is issued. P1 snoops the read and changes its state to S. P1 flushes the block across the bus where it is picked up by main memory in P3. Note that, unlike in the Dragon protocol, main memory does need to be updated because the protocol does not keep track of which cache is responsible for updating memory when it finally replaces the block. Then the read operation completes. Next, P3 writes A. This is a write hit, but because the line is shared, a bus update is needed. This bus update goes to memory as well as to P1's cache. When P1 snoops the bus update, it updates its cache. Meanwhile, P3's write completes, changing the cached value to 3. Both P1 and P3 remain in state S, and the write operation completes. Now, P1 reads the value of A from its cache. This is a read hit, so no bus activity is needed. P3 reads A from its cache. This also is a cache hit, so the cache simply returns the data. No bus transaction takes place. Now, P2 finally gets into the act by issuing a read for A. Since it's a cache miss, it requires a bus transaction, namely a bus read. P1 and P3 flush the block out on the bus, where P2 picks it up. Since the shared line was asserted, P2 changes into state S. The read operation is complete. Now all three caches have valid copies of the block in state S. This table shows which caches have the block in which state after each instruction. The first difference we notice from Dragon is that when P3 reads the line, it goes into state S, not into a special SM state. After P3 writes the line, it stays in state S instead of going into SM. And when a cache-to-cache transfer takes place, the data doesn't necessarily come from the last cache to write the line. This completes our consideration of the Firefly protocol.